Hey, it's Cooper Codes. Today we're going to be taking a look at the Leetcode problem, sum of left leaves. This was recently a featured daily problem on Leetcode, so I thought I'd go over it and kind of explain my solution. First things first, we can take a look at their example to get an idea as to how we can solve this problem ourselves. It's important to realize that in this example, the left leaf nodes are 9 and 15. And so we can take a look at these and kind of answer the question, what is a left leaf node? When thinking about what a left leaf node is, we can kind of divide it into two different problems. The first one is, what is a leaf node? Well, a leaf node is a node that has no children. So you can see in this example over here, we have 9 and 15. 9 has no children, 15 also has no children. And then the other thing we have to consider is, what is a left leaf node? So a left node is a node that is left to the node above it. So that's kind of the simple way of thinking about it, is a left node is to the left of the node above it. Something important to recognize there is that our root node technically can't be a left node if you think about it, because there's no nodes above it. So let's take a look at a simple binary search tree to see how we can take a look at what a left node actually is. So we can make a simple tree here, maybe put the value 3 here. To the left, we can say 5. To the right, we can say 10. And so in this one, we can see that the left leaf node is going to be this 5, but it's important to think about why. So we can look at this 5 and we can see that a leaf node is a node that has no children. So it checks off that constraint. The 5 has no children here and no children here, right? And then a left node is a node that is to the left of the node above it. So we have 3, and you'll see this is going to the left, and so it also checks that constraint. In our solution, we're going to want to try and solve the problem in a similar way to how we just did it on the paper here. We can kind of simplify this problem by thinking about an algorithm that's going to work at every single node. So we looked at the 3 and we saw that this 5 was a left leaf node. It's important to think about why. So from the 3's perspective, we know that we can check if there is a left node. So for example, if we're over at 3 and we're going to 5, we can say, okay, we're at 3, there is a left node. And then we can check if that left node, the 5, has no children. And that checks both of our basic constraints here. It's a leaf node is a node that has no children, and then a left node is a node that is left the node above it. And so if we're at the node above it, we can kind of think about it like this. We're at this 3 and we can check the 5 to see that it's a left node. And then the final part of our algorithm that's probably the most important is, if it is a left leaf node, so meeting both constraints, add to a total sum. All right, so hopefully this gives you a basic idea of how to approach this algorithm and kind of understand things. Let's get into the actual Leetcode and code this out. All right, so now we can actually get into coding some Python here to help us solve this problem. So the first thing we're going to want to do is think about a recursive solution to do this. The simple idea of considering recursion when you're looking at a binary search tree is that you start with your root node and then you make decisions based on the value of that node as you move through. So as it becomes, the dot left, the dot right, as it moves down, you make decisions based on the new value of your node as it's moving down. So let me explain that some more. First of all, we're going to want to make a recurse function that passes in the node, whatever the current one we're at is. All right. And we'll just get this done with early. We're going to want to recurse based on our root node first. So it's going to start at the 3, and then if 3 has a dot left, for example, it's going to go there. If 3 has a dot right, it's going to go there, but that kind of all depends on our logic. A base case we can kind of set up here is if node is equal to none, we can return 0. This is going to be important because of how we're going to chain our recursion statements at the bottom here. And let's just do that. So pretty much we're going to do something like this. Return recurse of node.left plus recurse of node.right. So as you can imagine, recurse of node.left, let's just look at this 3, right? And let's just keep on going through the dot lefts here. We're going to say 3, okay, go to the dot left. Okay, we're at 9. Now at the 9, go to the dot left. Eventually under this 9, there's going to be a 0 there. And so at that 0, we can kind of see that it's going to pretty much say 0 plus 0, and then this becomes 0, and then 0 plus 0, and then 0 up here. There are better videos out there explaining recursion in depth, and so I can make some if wanted, but this is just a basic idea of how we're going to solve this problem. And then we're going to pretty much see if there's something we can add on top of these zeros, because right now we have no other logic besides just 0, 0, 0. It's going to be 0 plus 0 plus 0 plus 0, right? And so now let's take a look at this comment I put up here. a left leaf node meets two constraints. It has no children nodes, and it is the left node to the node above it. So if we're at the node above, like in the example from the whiteboard on before, we can say if node.left, which means the node.left exists, and we're going to make a little complicated statement here, that node.left.left is equal to none, and that node.left.right is equal to none. So if you were to look at this 3 example, if we're at the 3, this 9 is the node.left, right? Then this 9's node.left.left is going to be the value to the left of it, which is none. And then this node.left.right is going to be the value right here, which is also none. And we know that this 9 is a leaf node because they tell us pretty much here. And so what we can do is do something like this. Add is equal to 0, and then add plus equals node.left.val. And then in our return statement, we can chain this extra addition. So if this statement becomes false, add is still going to be 0. It's not going to change our overall value, right? But when we add the node.left.val, it's going to put this, whatever value of this recursion statement here, or whatever value of node.left is here, right? It's going to add that to our overall recursive addition. So in that happening, you're pretty much going to have, 9 plus, 0 plus 0, which is going to have a 9 that's going to kind of bubble up in your recursion. So this is pretty much going to work right here. Let's see, we can run this and we can submit this, and yeah, it gets a pretty good runtime. Hopefully this video was helpful in kind of understanding the basic concepts here. I know I didn't go super in depth into the recursion and how it actually bubbles up, but I would recommend, doing print statements and kind of understanding how it's actually working that way, and kind of seeing how these node.lefts eventually become 0, for example. A great thing to do would be when a print, whenever it equals node is equal to none, print here inside of this if statement and kind of see how many zeros are being returned. And yeah, hopefully this video is helpful. Thanks for watching.